Well, good afternoon, everyone, and welcome to today's joint EOL M-Cube seminar, for which I'm pleased to introduce Dr. Virendra Ghate. Dr. Ghate received a bachelor's in mechanical engineering from Nagpur University in India before pursuing his master's and doctoral degrees in meteorology from the Rosenstiel School of Marine and Atmospheric Science at the University of Miami in Florida. His graduate focus includes characterizing drizzle under stratocumulus using Doppler radars, as well as turbulence and mass transport in stratocumulus clouds. Dr. Ghate's scientific tenure has included appointments at Rutgers University, the University of Chicago, and as a guest scientist at Max Planck Institute for Meteorology. Virendra is currently appointed as a principal atmospheric scientist at Argonne National Laboratory, where his primary focus is on marine boundary layer stratocumulus and shallow cumulus clouds and wind resource characterization. His academic career includes advising of undergrad and graduate students, as well as a number of postdoctoral fellows, and service on an impressive number of conference and working group committees. Virendra has participated in over 10 field campaigns, including airborne, shipborne, and ground components of such projects as RECO, Vocals Rex, CPS, SETS, and CSET, the latter of which utilize the NSF Gulfstream 5. His field endeavors have culminated in more than 200 hours as a flight scientist and more than 8 months of time at sea. On that note, please join me in welcoming Dr. Ghate for his seminar, Turbulence and Cloudiness and Cumulus-topped Marine Boundary Layers.
Thank you. It's very flattering introduction here. Thank you very much. Before I begin, let me thank Vivek and Sarah for inviting me for the seminar. It's a big honor to be here because in my field, you can trace the roots of the knowledge, all the cloud physics knowledge to the roots to this very organization. All the papers from this organization are sort of pioneer papers for cloud physics. That's a pretty big deal. Before I begin, also let me acknowledge my co-authors for this work. The publication just came out about 2 weeks ago in Journal of Applied Meteorology and Climatology. It's a pretty nuanced thing. And so the co-authors are Dave Turner from NOAA. He just works down the street from here. He's an expert in Raman Lidar's interferometry and also now weather modeling. David Meacham is a professor at University of Kansas. He's an expert in aerosol cloud interactions and large simulation models. Jonathan Giraud is a scientist at University of Wisconsin in Madison, and he's an expert in instrumentation and also interferometry. And Vince Larson is a professor at University of Wisconsin at Milwaukee, so it's a separate branch of Wisconsin University. And he's an expert in cumulus parameterizations for large-scale models, so a lot of long history for that. And Jessica Kleis, she's a professor at Lewis and Clark College, that's in Oregon, and she helped out with case identification and also the total sky image analysis. It was pretty good. And before I go further, also let me acknowledge my funding agency. That's the Department of Energy's Atmospheric System Research Program, ASR. And most of the data we use in this work is from the Atmospheric Radiation Measurement, or the ARM program. All right. So the first question is, why study shallow cumulus clouds, especially over the oceans or over the marine locations? Shown here is a cloud atlas image, so average cloud fraction from surface observers as made by the Warren Cloud Atlas. So sort of a 50 plus years of averages go into this, making this figure. And you can see the cumulus cloud fraction being pretty high in the sort of tropical regions, subtropical regions, etc., and sort of tapers down as you go towards polewards when you have more stratiform sort of cloudiness in this case, right? It's pretty interesting. But needless to say, over all the global oceans, we see this cloud type. That's the first thing to note from this figure. Second thing to note is that the site at which we are using the data from is located in this star here, which is exactly at the transition zone. So you basically sometimes get stratiform clouds coming from the north, or you also get these shallow cumulus clouds, sort of southerly wind conditions or largely southerly wind conditions, just in case. On the right-hand side, I'm showing you a visual satellite imagery from one of our cases from Moody's. And you can see these clouds as sort of white cotton balls over this dark ocean. The scale here I'm now showing is about 200 by 200 kilometers, right? So pretty large in here. And you see these clouds as streaks. You can see them sort of organized very nicely as in lines in this case. Other thing to note is that you have changes in cloud fraction. You have some higher cloudiness in here, then you have lower cloudiness. You can again get higher cloudiness in this case, again lower cloudiness around. So you have just changes in cloudiness that's happening. And there has been a lot of work recently done using large domain LES models where they have shown that these changes in cloud fraction is sort of caused by changes in water vapor mixing ratio at these scales. So different sort of scales, water vapor variability that is causing these changes in cloudiness and also this rain from these clouds. That's one thing. So these clouds are important for radiation, also water cycle, right? So two things I want to mention. So how these clouds work? So this is nice simple schematic from Louis and Nuance's paper from 2015. It's an overview paper came out some time ago, but it's pretty nicely summarizes how these clouds work. So we have an ocean below, which is a little bit slightly warmer than the air above it. And that sort of sets up this transport of mass, momentum, and heat and moisture from the surface up. So you have surface buoyancy generation, FB in this case. And you generate the buoyancy that sets up the turbulent eddies, and you have this formation of this mixed layer in this case. Shown here are profiles of water vapor mixing ratio, which is Q. So you have a sort of a small inversion right here, then you have a sort of stable layer, then you have another inversion right here, right? So mostly people call this as a mixed layer inversion, and this is called a trade wind inversion in this case. And we sort of see similar conditions in the ENA site. Now, the mixed layer depth here is sort of shown by h in this case, capital small h. And so if you have an eddy that has enough juice or enough velocity, you have a transport of mass from the mixed layer up above it. So you go above the lifting condensation level or LCL, and you have condensation and forming of these clouds, right? So you have this cloud formation as you go up. The clouds can be tall and skinny or can be short and wide in some sense. You can have that. That's one thing to note. Also, unlike stratocumulus, when you have 100% cloud fraction, these clouds have gap in between them, right? So you can have actually gaps around the cloud. They are not 100% cloud fraction. That's one thing to note. Last thing to notice in this case is that you also have entrainment happening. You go from transfer of mass from the above the mixed layer into the mixed layer. That's E, capital E in this case, of mass transport here. And then the whole thing, which is a cloud mixed layer sort of complex sort of underneath a descending branch of Hadley cell, that's the WS, which is the sort of large scale substation that's happening, right? So that's how it works out. So it's pretty cool. We have sort of this sort of simplified model has been used for several decades now to understand cloud fraction and how these clouds work. It's pretty standard. So a lot of questions happening in this case. What is the difference between the clear and cloudy eddies? Why some eddies form clouds, why some don't? That's the main question. Are they more moist? Are they have more vertical velocity, etc.? We don't know that. That's another question. And what is more important, mass flux for cloud fraction or its entrainment? How does mixed layer changing both of these, mass transport, etc.? There are many questions in this case. So for this particular work, we had 4 science questions. Number 1 was how does cloudiness relate to number of clouds and cloud width, right? So if you have an increased number of cloud fraction in certain volume, do you get more number of clouds, more number of cloud elements, or just wider clouds, right? So you can just have wider cloud, get higher cloud fraction. You can have that, number 1. It will be unfair if I don't credit the question to Wojciech Grabowski. He was our reviewer for one of our SFA panels, and he sort of asked us to probe that. So that's coming from that review panel, so it's pretty good. Second question we had is how does the transport of clear air eddies differ from cloudy eddies? So as I mentioned, what does the cloudy eddies have that the clear air eddies don't that leads to formation of clouds? That's the second question we have. We want to understand that. Third one is sort of very generic and has been used many times to understand things. What is the relationship between cloudiness and mass flux? So cloud fraction and mass flux, how they relate, and also mass flux and entrainment, how they are related to each other. So that's sort of third question we plan to address. And the fourth question we have is how does cloudiness, mass flux, and turbulence changes or varies with mesoscale moist and dry patches, right? So if you have a moist and dry patches, water vapor changes, how are these things changing for these two conditions, right? What are the changes in those things? So, all right. So to address these questions, because I work at a DOE lab, we have to use DOE data. So use data from DOE, one of the site here. So many of you probably are familiar with the ARM program, that's Atmospheric Radiation Measurement Program. They have 3 fixed sites and 3 mobile sites. One of the fixed sites is called Eastern North Atlantic. It's in the central sort of a, or central or eastward North Atlantic, where you have this group of islands called Azores, and you have 3 group of chain of islands. One is on the west side, central group of chain, and then the east side in this case. And the site is located at the island of Graciosa, which is the northernmost island of the central group of islands, right? That's where it is. The site is operational since 2013, so almost 10 plus years of data, continuous operation, which is pretty substantial in my mind, and is heavily instrumented. So I don't want to go into details, but they have multiple radars, scanning, telepointing, multiple wavelength radars, multiple lidars also, again scanning, telepointing, different wavelength lidars, radiometers again, all of them together. They also have balloon launches twice a day, sometimes more. They also have aircraft field campaigns for intensive operational periods, etc. That's there. They also have detailed aerosol measurements. So you basically get aerosols from a pipe into a container, and then you measure aerosol sizes, mass, and chemistry. So all the things are there. So pretty heavily instrumented, pretty nice site for marine cloud studies. So in the bottom right panel, I'm showing you the lat-long map of the altitude of the island. So the island is about 10 kilometers by 10 kilometers long, so it's not that big of an island, but then it does have peaks about 400 meters high. So you can see about 2 peaks here and another one here. They were formed by volcanic eruptions long time ago. That's just how the topology is. So, and there are about 5,000 people who live on this island, and they live and they pollute just like all we are doing. So we did past studies again, 2 studies where we showed that if the wind conditions are not from this sector, so not from this marine sector coming from the south, then they are affected by the island heating, because we are actually looking at land is heating up and affecting the air above it, and that is forming clouds, changing thermodynamics, all of those things. So that's a problem. So we have to use for the rest of the analysis, we only use data from this marine sector, that's the northeasterly sector in this case. So sort of constrain our observation to marine conditions. The study was very nice, but the unfortunate outcome of this was that only about third of the time we get winds from this sector, right? So clearly our 10 years of data then only became 3 years of data, right? So because we don't have conditions for marine conditions all the time, that's a problem. So that's a big hit for us, but it is what it is. All right. So from all the 10 plus years of data, we were only able to identify 8 cases. That's the consequence, right? So I'm showing you, 13 plus years of data now, and we only have 8 cases, which is very kind of sad in some sense, right? And I was hoping to have hundreds of cases for that matter. And the reason for that is, first of all, the marine sectors really sort of drops down our sampling. You get about 1/3 of a sample size only. That's number one. Second is that we had to make sure that all the instruments are working at the same time. So that's the vertically pointing radar, the Doppler Lidar, the Raman Lidar, etc. All of them are working, and that was not the case. We actually had instrument breaking down one time or the other, and that sort of broke our thing. So we had about 8 cases. Some cases were about 10 hours long, some were day long, so it's pretty big sizes in this case. Total case time was 141 hours, so it's really not that small, but not that big either. So it's pretty good. We had some substantial averages. And then from the total sky imager and the radar, we were able to count number of individual cumulus clouds within them, and we had about 603 marine shallow cumulus clouds. That's pretty good. So shown here is a time height image in the top panel. So x-axis is time. You go from about 7 a.m. in the morning to about 8 p.m. at night. So only daytime conditions. And I'm showing you radar reflectivity in colors, and the dots are cloud-based height from the ceilometer. That's a LiDAR. There's dots in here. The middle panel here is again time on the x-axis, height on the y-axis, and I'm showing you the vertical air motion from a Doppler Lidar and radar together. That's pretty good. And lastly, below we have the total sky imager, just a mirror with a camera on the top and taking photo every 30 seconds. Pretty neat in some sense. So let's see if we can play this movie, which is I'm not able to play, which is perfect. All right, good. So now, by the way, the vertical line here shows when the image was captured. So you can see in this case, pretty good. So you have some clouds here, then some gapping clouds. then some more clouds, then again no cloud, right? So I can drink some water. Yeah, it's good. Then you have some more clouds, and then we have this big cloud coming up, has some rain in it, right? So it's pretty good, some rain falling down. And then you have nice clusters in again, more clouds in here, sort of going back and forth. There are a few things I would like to highlight in here. Number one is the cloud base height is pretty constant, right? So you can see just the black dots is about 500 meters. So these sort of typical Bomix type shallow cumulus we are looking at in here. It's pretty nice for us to see. Second thing I want to mention from the instrument side of point of view is that the LiDAR is able to capture, so LiDAR sees all the clouds. It's pretty sensitive to liquid drops, but the radar also sees all the clouds, right? So we rarely have an instance that the LiDAR sees there is a cloud, but the radar is missing it. So radar is very sensitive. If you would do this study at a other location, that might not be the case. The radar is actually very sensitive radar, so I'm pretty happy with that. Third thing I want to mention in the top panel is that you can almost see the Mesoscale clusters. You also see a cluster here, then you have a gap, then again cluster here, some gap, another cluster here. So you almost see the Mesoscale organization of clouds in the radar image in this case, right? Pretty good. The middle panel, you can see vertical velocity, positive is going up, negative is coming down, and you can see some very strong vertical air motion. It's about 1 meter per second updrafts, even though the clouds are very thin, right? So that's an interesting thing, very strong updrafts happening in these cloud systems. You don't see that much of a strong downdrafts. That's a thing to notice. And that means that sort of a very strong updraft, you have a broad, very weak downdraft. That's a system we are sort of looking at in this case. Pretty good. So on average, about 558 meters, that was a cloud base height for our case, which is pretty good. The clouds were only 99 meters thick, so only 100 meters thick, which is not that thick, about 3 radar range gates when you think about that. It's pretty thin clouds. And the chord length or the width of the clouds was 500 meters. It's pretty substantial in my mind to capture that. And very consistent with previous studies, the hourly cloud fraction was about 12%. So very small, very thin, wimpy clouds in this case. Pretty good. All right, so moving forward, we had to do retrievals. I want to quickly mention the retrievals we are doing. Number one, we got cloud boundaries, so cloud top height, cloud base height, and also the cloud width. That is done from the data from vertically pointing cloud radar and ceilometer. That's the Ka band radar, very sensitive Doppler radar, so you can do retrievals at a very high confidence. Second thing, we retrieve vertical air motion. That was done using data from vertically pointing radar and the Doppler Lidar. So different Lidar, that's a 1.58 micron wavelength Lidar. So it gives you much more substantial returns in this marine environment. So that was helpful. And third is we derived thermodynamic profiles. So we had balloon launches twice a day, one at 0 UTC, other one at 12 UTC, which is pretty good. They were Raman Lidar operated at the site. We spent almost a year plus of our effort to retrieve water vapor profiles. It's 10-second, 30-meter resolutions, pretty high resolution in my mind to derive that. And a lot of things went into that. And I don't want to bore you guys, but yeah, there's a lot of instrumentation work was done for this thing. And lastly, we did the TROP-OE retrieval, that's tropospherical optimal estimation framework, which is combining Raman Lidar and AERI data set. And this is done by Dave Turner. He has a sort of a algorithm for doing that. That gives you profiles of water vapor mixing ratio and relative humidity at a 1 minute and 30-meter resolution. So pretty good resolution, and also from surface to 15 kilometers. And that is done useful for Mesoscale organization sort of work that we did later on in this paper. All right, I don't want to spend too much time in here or this figure, but just want to mention that these are average radiosonde profiles, this is potential temperature theta, water vapor mixing ratio R, and wind speeds. I just want to highlight that as I showed you in the schematic before, you almost see this nice mixed layer here, a small inversion. You see a nice, again, stable layer and another trade wind inversion in this case, right? So it's pretty nice, substantial in my mind. And we are sort of, we are proud of this kind of stuff because we are able to use it. Data set that sort of agrees well with the theory or we had with previous efforts. It's pretty good. Second thing I want to mention, we don't see that much of clearer inversions in the mixing ratios, but that's how it sort of works out because the weather in this case, the vapor in this case actually changes pretty fast. And the third thing I want to mention is that the wind speeds actually is almost constant with height. So we actually don't have any wind shear in the mixed layer. It's a light different than the continental mixed layer where you have some wind shear. So we don't have turbulence from the wind shear case. All is buoyancy driven turbulence that we are looking at.
Is that a property of cumulus?
Can you repeat?
Lack of wind shear, is that a cumulus property?
It's a property of marine cumulus mostly. For the continental side, you have land mass, and that's what changes the wind speed, and you have some topography effects there. In this case, you have flat, right? So nothing there. So yeah, and also we were sort of able to select cases that is much more uniform. So we didn't have any large scale advection coming in or some frontal passages. That's sort of a restrictive analysis in this case. Thank you for the question. Yeah. All right. So. Okay, so are the retrievals good enough? That's the question I have. And a lot of people, they start doing retrievals and they are like, okay, this is good, and we start run with it, And we had to make sure the retrievals are good enough to answer the science questions, right? Because right now what we are looking at turbulent fluctuations of mixing ratio and vertical velocity. And these are hard to capture, these are hard measurements, hard retrievals to do. So shown here is frequency on the x-axis and the power spectrum density on the y-axis. So just looking at the 50 standard things. And the black line you can see is from the Doppler Lidar, vertical velocity W at 300 meters. And you see it's nice flat, and this comes down perfectly with the -5/3. It is good. One of my co-authors, he basically looked at the figure and he said, well, even Kolmogorov would have been proud of this curve, right? Sort of follows the -5/3. It's pretty cool thing. Unfortunately for us, we spent almost a year plus for the water vapor retrievals from the Raman Lidar, and this did not work well, right? So you can see the Raman Lidar wide field of view mixing ratio, and sort of starts to go down, you get a flat line, right? Same thing you see from the narrow field of view. So it's exact same thing for the full field of view. And we spent some time, why is it happening? It's problem with our retrieval, something with the instrument, etc. And that was not the case. What we figured out finally is that the Raman Lidar has an instrument noise, which is very high, and that is giving you this perturbation symmetric about the mean that we just cannot filter out. They are changing over time, etc. Just cannot do. So unlike some previous studies, not mine, some other people, they have done profiles of latent heat flux by combining data from vertical velocity, from the Doppler Lidars and the water vapor from the Raman Lidar. We cannot do that for this case, right? So that's a problem. So almost a year plus of work, and we are on the other side of the result here. It's not possible to study fluctuations in water vapor mixing ratio for us. The earlier goal, as I mentioned before, was that to understand if the clear air eddy or the cloudy eddies were more moist or had more moisture than the clear eddies. We cannot do that work unfortunately for this data set, but it is what it is. All right, but we can do other things. So we can move forward in this case, right? So let's look at the first science question. How does cloudiness relate to number of clouds and cloud width? So essentially, if you have more cloud fraction, does you have more number of clouds, or you just get wider clouds, right? So in here, the x-axis is cloud fraction in both plots, and the y-axis here is cloud chord length. So it's the width of the cloud, and the y-axis here is number of clouds, so number of cloud elements within them. And I'm showing you reporting here the correlation coefficient, which is about 0.53 for the cloud width, or 0.78 for the number of clouds in this case, right? So, by the way, both correlations are statistically significant. We had a 10,000 sample bootstrapping method for this case, so we actually have more confidence in these correlation coefficients. So it sort of says that the predominant control for cloud fraction is actually number of clouds. So you have more cloud fraction, you get more number of cloud elements rather than just wider cloud elements, right? That's the one thing. It was not really sort of 0 or 1 game, sort of just says one is more important than the other, but both are kind of equally important. We cannot do PDFs of water vapor mixing ratio, but we can do PDFs of vertical velocity because we are capturing turbulent fluctuations in this case. So shown here are PDFs. So x-axis is vertical velocity, and y-axis is the normalized PDF in this case. One is for clear air samples at the cloud base, and the other is cloudy samples, right? So at the mixed layer top. And you can see it's fantastic. The clear air eddies are almost symmetrical, right? So about 0.4 in this case, mean of 0. So the clear air eddies sort of balancing out the mass in this case. The cloudy eddies are positively buoyant, so they are actually 0.3 or 0.4 meter per second mean. So there's buoyant plumes going up, which is pretty nice. Cloud eddies also have a positive skewness. You can see about one more than one here. You actually don't see less than one in this case. So that's a positively skewed distribution. And lastly, I want to mention also that the cloudy samples also have downdrafts in them, which is kind of neglected in some of the models. So the cloudy downdrafts can span about 0.6 or 0.8 meter per second. They are much stronger than the clear air downdrafts. So it's another thing to sort of notice in this case. Vince Larson, who has a long history of developing cumulus parameterizations, he uses PDFs and joint PDFs of vertical velocity. And he was pretty stoked about this because now you can have one PDF which is Gaussian for clear air samples, another one is skewed for cloudy samples, and you can sort of simulate that and use that in large scale models. So that's the plan in the future. All right. So for the rest of the talk, I'm gonna focus on mixed layer budgets. So I'm gonna lay out the budget framework in this case, sort of we understand that. So H is a mixed layer depth in here, which I mentioned before. So that's we do the budget of the average mixed layer. So the number of the mass we have in this mixed layer, that's what we are looking at in this case. The left-hand side is the local change in mixed layer depth, del H by del T, plus the advection term, which is just this advection. And that is essentially balanced by the large scale subsidence, WS, entrainment, and then the updraft pass flux from the clouds, right? That's going up. It's a nice framework that has been used by, in here I put a reference by Rafaela Vogel, has been used by other people also. It's pretty well established thing. And just to revise, the mass flux here is actually just a number of eddies or fraction of occurrence multiplied by strength of the eddies, right? So you can have a cloudy updraft mass flux. So you only get number of cloudy updrafts and then number of their strength, and you just sum it up for the whole distribution. That's how it works out. So you can do the same thing for cloudy downdrafts, clear air updrafts, and clear air downdrafts. Right? You can do all of those because we have measurements for that. So that's exactly what we did. So in here, we have a bigger equation now. Again, this left-hand side is the same. The del H by del T term, that's local change in mixing in the depth of the mixed layer, plus the advection, which is balanced by large scale subsidence. And now we have four terms in here. So one is a cloudy downdrafts. So which I mentioned before, clouds have downdraft, that's number one. That's adding mass to the mixed layer, that's a positive term in this case. We have clear air downdrafts, that's we showed before in the PDFs. That's again adding the mass to the mixed layer. The cloudy updrafts, that is subtracting the mass from the mixed layer, that's a negative term. And you have clear air updraft, that's again subtracting the mass from the mixed layer, so negative term in here, right? So we have four terms in this case. So normally we use this cloudy updrafts, which is cloudy updrafts here, which is exactly what shown here in this case, or what is shown in this figure that's related to cloud fraction, sort of works out pretty well. This term here, which is cloudy downdraft, is kind of ignored in many places. Many sort of models, etc., ignore that, and there is good reason for that, and we'll get back to it in a few slides. So we ignore that. And then lastly, we have these two terms, clear air downdrafts and clear air updrafts, right? So now, depending on who you talk to and which literature you follow, we actually have two views of entrainment, right, in this case. One view is that everything that's going up is clouds, so there is no clear air downdrafts at all. So even clear air updrafts at all. You only have downdrafts in the clear air, that's entrainment, that's one view. And the other view is entrainment is actually sum of these two, which is clear air downdraft versus clear air updraft, right? So sum of those two, and this comes out to be negative, right? So that's the main thing. So you have two views in this case, and we'll probe that in few slides in this case. Do we have any questions on this? Maybe because I want to, yeah. Oh, go ahead.
Referring to entrainment with respect to the cloud, or entrainment with respect to the two layers?
It's entrainment towards the two mixed layer.
Okay.
Yeah. Please, sorry.
Yeah, going back to a little closer to the beginning,
Here.
you showed this spectrum of
The frequency pressure?
mixing ratio.
Yeah.
And you showed it flattening out.
Yeah.
So is it random noise that's giving you that, or what is it?
It is random instrument noise, yeah.
Because if it's random noise, if the instrument responds quick enough, you can still do fluxes, even if it's full of noise.
Yeah, we tried that. Don Henshaw has a method for that, which is autocorrelation, right?
Well, listen to him. No, don't
Which is you, right? I pitched it perfectly, didn't I? Yeah, thank you. Yeah. All right, go ahead. Yeah. We tried that. We did the M11, M12, and we also did all of those. Dave helped out with that, so as you know. So it's hard. I had to do it otherwise.
Curious if you could just tell us how you defined eddy strength.
Eddy strength, yeah.
Yeah.
So we have 1 second measurements of vertical velocity, right, from the Doppler Lidar. So we use that. So basically, it's a very good question. We have bins that go from -6 meter per second to +6 meter per second in intervals of 0.2, and then we use those. And for each bin, I'm counting how many eddies we have for certain strength, and then we add them up at the end to calculate mass flux. Thank you for listening, by the way. I'm happy people asking questions. It's good. Any other questions? Because I think this is it, because that's the last few slides are just on that essentially. Okay, thank you. Yeah. All right. Sorry. So okay. So first question we have, and we have not. Okay. Sorry about that. I don't know. Okay. Good. Here. So the question we have now, before we go into the mass flux budgets, we have to understand what is controlling the mass flux. Is it really eddy strength or eddy fraction, right? So we have number of eddies that is controlling the mass flux, or is the strength of the eddies that is controlling the mass flux in this case, so eddy count, which I'm mentioning here. So shown here is a downdraft mass flux on the x-axis, a downdraft mass flux on the x-axis here, and the y-axis is the downdraft strength and the number of downdrafts, the sigma down in this case. And the same thing in the right-hand side, we have the updraft mass flux in here, and you have updraft number, the strength of the updrafts, and the number of updrafts right here, right? And just by looking at the figure, you can just see that we basically see a very nice correlation in the clear air cases, right? So red, we see a nice correlation between the W and the mass fluxes, pretty good. But you don't see any correlation at all. The sigma down is almost flat, right? So that's an interesting thing. So essentially, for the mass flux, mostly you want to know is the strength of the eddies, not the number of the eddies. That's the more important thing. The correlations here are not that high for the cloudy cases, because you just have less number of samples and it's a more dynamic case. But you do see sort of a positive correlation in this case for the updraft mass flux. Downdraft cases, you actually don't have that many samples. These three are actually controlling most of it, otherwise just more scatter. So that's the case, but mostly you can see that eddy strength is more important than the number of eddies for mass flux calculation, right? That's a mean. And it's a fundamental issue, because that sort of drives what we should be paying attention to when you're modeling these clouds in largely or in atmospheric models in this case. Okay, all right. All right, so second question, again, I apologize for the messy figure, but I think it's important in this case to have scatter plots all over together. Let's look at the relation of updraft mass flux to cloudiness, right? So as I mentioned before, people have used updraft mass flux to relate it to cloud fraction. That has been done for many years now. So shown here is updraft mass flux on the x-axis here, and the y-axis is cloud fraction, right? And you can see the cloudy samples, only cloudy updrafts I'm looking at here. You see a fantastic correlation in this case, the blue crosses in this case, and you can see that's good. And the correlation is about 0.82, which is pretty high in my mind, and that's also statistically significant. The interesting thing here is that clear air updrafts. We have clear air updrafts in these cases, which is some people just ignore it or is sort of not considered, and they really have no correlation. You basically just see a blob of this red in between, right? It's pretty good. They're just doing what they want to do in some cases. The correlation quotient is about 0.05, so negligible correlation, which doesn't exist. And then the sort of the effect of this is that when you add both of them up, you basically get a black line, the total updraft mass flux. You have a reduced correlation in this case, right? So the point I wanted to make for this figure is that we have to be really careful to look at the updraft mass flux, because the clear air part can just skew our distribution and then reduce its dependence on the cloud fraction in this case, right? So the cloudy updraft mass flux can be used to derive cloud fraction, which is pretty substantial. However, the total updraft mass flux is dominated by non-cloudy processes, right? So because the clear air value is about 0.05, which is much higher than the cloudy part, right? So that's the important to notice in here. All right. Lastly, we go to entrainment. Yeah. So as I mentioned before, in some old formulations, the entrainment rate is just used as a clear air downdraft mass flux. So how much air is coming down from clear air. That's sort of old school, or not sure old school, but like a, yeah, old sort of thing. And in the recent version, they will say, well, it's a sum of the two, which is a clear air down minus clear air up, right? And the hope in this case is that these will be net positive, so it's also adding mass to the mixed layer. That's how it works out. So the widely used entrainment parameterization is actually this one here, which is showing the figure, so the equation here. We have entrainment velocity, WE, A is entrainment efficiency, this is surface buoyancy flux, W prime theta V prime, and delta theta V is inversion strength, right? So we have that, all of these things. And the entrainment efficiency is sort of fixed from a LES model simulation done for DICOMs and STEX, which come from 0.43, which is a different value. So it's there. Now, for our work, we have independent measurements, right? So we can measure delta theta V. We have measurements of buoyancy flux at the surface. And then the WE, we can relate it to the clear air downdraft or also the sum of these two, right? Clear air down minus clear air up. We can do that. That's exactly shown in these plots in this case. So the x-axis here is sort of this value here is the ratio of the surface buoyancy flux to the inversion strength. And the y-axis here is just downdraft mass flux. And when I made this figure, I was pretty, happy and surprised because the theory really holds well. You are basically getting observation from different instruments here, complete different places, and you see a nice slope in here. The correlation coefficient about 0.53. That's pretty good in my mind, given how the system we are looking at. That's there, but however, if you look at the scatter plot between the clear air down minus clear air up, you basically don't see any correlation at all, right? It's pretty scattered in this case. So the formulation as it stands now is only taking into account the sort of clear air downdrafts, not the sort of the sum of the two updrafts and downdrafts together. So that's the problem in this case. I just want to dive from the point. The entrainment efficiency in this case was 0.6. So that's the slope of the line, so to speak, in the left-hand side panel, which is much higher than the 0.43 used by other studies. And sort of the grand sort of conclusion from these figures is that the parameterization currently only captures the clear air downdraft mass flux, not the sort of sum of the two together, the updraft minus downdraft cases. All right. I don't want to spend too much time on this figure. It's want to mention that we looked at vertical profiles of mass fluxes, echo fraction, so cloud fraction, etc., and vertical velocity variance and skewness, because we have those variables. And it's want to mention here is that if you just look at this figure here, the total updraft mass flux is pretty high compared to the cloudy portion, right? So cloudy contribution to the mass flux is about 23% at the cloud base. So very low, I think the cloudy samples are really not doing much mass transport in this case. And the same thing was true for the variance of vertical velocity. The contribution of cloudy eddies to the total variance of vertical velocity about 33%, so really not that much. So this idea that the clouds are actually more dominant and turbulent than the clear air is really not holding true for at least for these shallow cumulus cases. We can go on for 5 more minutes. So we looked at mesoscale variability. We use a technique from Zhao and Betterton, 2019. They basically use a time series of water vapor mixing ratio at certain level, and you filter out any perturbations less than 10 kilometers and more than 50 kilometers, right? So you are looking at this sweet spot in between, and you subtract that out, and you get these mesoscale dry and moist patches between them. You get this perturbation, right? So from that, you're able to identify 29 dry patches and 25 moist patches from this case. These patches are about 2.5 to 3 hour long each. That's what sort of works out, so in time. And they are about 30, 40 kilometers in sort of length in this case. It's pretty good. Consistent what we found with previous work is that the cloud fraction in the moist patches was actually 29% and compared to 16% in dry patches. So you have much higher cloudiness in the moist patches than the dry patches that we expected to see. That's pretty good. The mass flux was also higher. So you had the moist patches had more turbulence, had more updraft mass flux, 0.09 compared to 0.06. And then also latent humidity was actually higher in the moist patches that we expected to see. So about 82% to 78%. It's pretty small, but it is what it is. The unfortunate thing, what we happened for this analysis is that because we had only lower number of samples, none of our results were statistically significant. So we could not do a thorough analysis in this case. The other problem we had is that I was expecting a very cool result, just like entrainment stuff, which we did not have. The cloud boundaries, chord length, surface fluxes were all similar for the moist and dry patches. So we could not see any big difference in these cases. So I just want to end here, summarize the results. How does cloudiness lead to number of clouds and cloud width? The analysis here suggests that cloud fraction changes were primarily driven by cloud number than not chord length. So you get more number of clouds when you have higher cloud fraction rather than wider clouds. That's one thing. How does transport of clear air eddies differ that from a cloudy eddies? That's another question we had, and unfortunately we could not do the moisture content analysis because of Raman Lidar issues, but we sort of tried at least. But we found that the cloudy eddies have had stronger updraft than clear air eddies. That's one thing to note. And then when we did the budgets of the mixed layer budgets for the whole cases, we found out that the cloudiness is controlled by cloudy updraft mass flux, kind of a nice correlation, while the clear air updraft mass flux were actually dominating the total mass flux, right? So that's the thing. The clear air updraft actually substantial and almost twice as much as the cloudy updraft mass flux. That's a sort of result there. And the last one was entrainment parameterization, only captured the clear air downdraft mass flux, so it was not able to capture the venting of the air by clear air eddies above the mixed layer. That is also important. So the sort of grand conclusion, if you want to say sort of one line conclusion in this case, is that the clear air eddies that exist between the cloud elements, they probably should not be ignored. They do substantial transport. They have updrafts, so they actually vent air from the mixed layer above the entroposphere. That's sort of venting effect that's happening. That's really not sort of accounted for many times. And they also are doing substantial transport in terms of downdraft. That's entrainment. So adding the mass in this case, pretty substantial in this case, have to do. So the biggest shortcoming of this work, or criticism I would say of this work, is that we only looked at one site. So we don't know, the results are only for the shallow cumulus clouds, also only marine cases in this case. So we don't know. We don't know that's the only case. So we plan to address that by looking at cases from continental shallow cumulus. Mostly we plan to look at the shallow cumulus clouds from the Ghate National Forest site. It's in Alabama. It's a forested site, so a lot of shallow cumulus, very high humidity. So that's the plan going forward. Thank you.
Thanks, Virendra, for that interesting and thought-provoking talk. Reminder to those online, you can enter your questions in Slido, and we'll read them out here in the room. What questions do we have?
So your observations are a little bit inland from the ocean. Have you looked at whether there's any effect of the island on your measurements?
Yeah. So it's not that far from the island itself, the site. From the ocean itself. Let me go back to the photo we had. Yeah, right here. You can almost see the ocean from here. This is looking out east on this side. So it's there, and so you can almost throw a stone from the side to the ocean. It's not that far from the northerly edge. From the southerly wind conditions, we do see substantial higher turbulence. The island is much warmer than the ocean, and that's why the mixed layers are much deeper, and the variance of vertical velocity is almost twice as much in the southerly wind condition than the northerly wind conditions.
Yeah.
So yeah.
Right behind me. Oh, okay.
Thanks for the talk. I was just wondering whether you had, and I might have missed this, whether you had any issues with attenuation of your LiDAR signal within even the shallow clouds, and how that might affect your partitioning between the dry parcels and the cloudy parcels.
Yeah, that's a very good question. I should have been clearer. I apologize. So the LiDAR signal does attenuate completely at the cloud base height. We don't see any, their clouds are optically thick, so we don't see above that. But we do have the radar that gives you vertical velocity inside the cloud. So we merged them together. They are just co-located like maybe 10 feet apart. So we just merged them together to get a seamless sort of vertical velocity in this case. That also reminds me one more point I forgot to mention in this case. The LiDAR really likes larger aerosol particles. And because the marine location is loaded with sea salt, it's a little bit bigger particles. So you can see we have returns above the cloud layers, in this case, which is very unlikely. If you look at the continental clouds, we rarely get a return at the cloud base sometimes. So it doesn't have that much juice in there. It's pretty cool. Thank you.
Great. We have Hugh, then we'll go online, and then Christina.
Great talk, Virendra. I'm interested in your results for the chord length in particular. So you showed the plot with a bunch of different values. Yeah, that one right there. So is this a mean or a median from each of the cases? What's being shown for that chord length, or what does that measure on the y-axis?
Fantastic question. Attention to details is pretty cool. That is mean cloud chord length for each hour. That's what we are looking at. Yeah. And the number of clouds is number of clouds, right? Yeah.
Okay.
We redid the work using median also to understand, and we had similar results.
Okay.
Yeah.
And then have you looked at all at the actual distribution of chord lengths? Interested in that. Some studies have shown a power law distribution of cloud size, some in exponential. I'm wondering if you've looked at that at all.
We have not, and we should. Yeah. I can circle back to you. We just did not have that much variability as we have done like Roll-Neger's papers, when they had all power law relationship. We didn't have that much, the clouds did not get that wide, I should say. So okay. to sort of, but we can look into that, sorry.
Okay.
Yeah.
Yep.
Great. You can pass to Christina. Bart Geertz asked, do you have spectra from LES models to see what the expected humidity and vertical velocity are for this environment?
I did not when I wrote the paper, but we do now because the LASSAO simulation, that's large simulation, a lot of cases have been just finished. And some of these cases were included in those. So we can look at that. And that's a great point. Thank you, Bart. Yeah.
Thank you for the presentation. I learned a lot. I'm curious about your thoughts on this binary approach for categorizing your profiles from cloudy and dry. And if you could you go back to the time series, while you were describing the story of this case, you were even saying, there's a sort of patch and a lot more distance between clouds compared to some that are more maybe clusters. And so I'm curious if you've dug into maybe like the entrainment properties where you might have cloud elements at a higher density versus where you have a big sort of pause in your clouds. Do you have any comments on that?
Very good question. Okay, so I do have thoughts. So to answer a short question here, and it is very hard to do. The problem here is, so let's look into that a little bit. This is a good figure. So our cloud base height is 500 meters, right? Okay. Now, let's just assume we have 1 meter per second updraft. Okay. So that updraft will take 500 seconds to go from surface to the cloud base, right? Okay. Now the horizontal wind speed is about 6 meters per second. So now, by the time you arrive at the cloud base level, you are almost 3 kilometers away from the surface when you started. You know what I mean? Yeah. So that's one aspect of this whole picture. That's one. So that's why when we looked at the entrainment rates, rather than looking at the whole thing, we only look at time series at the cloud base height itself. So we use the average cloud base height for each hour, and we look at the distribution of vertical velocity at that level only to see what is causing up and down draft changes. Okay, so in this, when you just look at one level, so the level was looked at because 2/3 of the changes in cloud fraction are only controlled by changes in the cloudiness at the cloud base height. So that's the predominant changes in the cloud fraction, right? And also changes of mixed layer depth. The other part of that is we in a way just look at the cloud base height level, we actually decoupled from the surface or anything happens below that, right? So it's either it's cloudy or non-cloudy in this case, right? You don't have anything in between. Did I answer your question maybe, or maybe not, I don't know. Yeah, sorry, yeah, okay.
No follow-up?
A nice presentation. Given that you got a range of instruments in that site, what you use to retrieve many other quantities, how do you quantify uncertainty? Because each instrument has some uncertainty when you measure the wind or humidity.
Yes.
Then I was wondering, in your scatter plot, you do a lot of scatter plots. What's uncertainty in those retrievals? Is there any percentage? Have you had a chance to do that one, or?
A really good question. So we looked at, uncertainty for Doppler Lidar is just a mean Doppler, just like our radar, right? So it's more driven by the FFT points you do, velocity bins, right? So this one has 250 points, and you go from -10 to +10. So it's pretty small perturbation we have. The more thing we are worried about for vertical velocity was that pointing errors. So when we assume the lidar is pointing vertically, it might be pointing off zenith. So for that, we actually looked at the averages, W for the whole thing, and we came out to be pretty close to 0 for each hour, So that's one. For Raman Lidar, as I understand it, it's always Poisson distribution for the water vapor, so we can actually calculate uncertainty for retrieved vapor, and we were about 25%. So anything uncertainty more than 25%, we threw those samples away. We didn't really use them. That's one thing. And the cloud thickness and chord length, they were just time samples of radar returns, right? So there is no inherent uncertainty in this case. The range resolution is about 30 meters for the radar, so it's pretty good in my mind.
I see. Okay, that's a very challenging retrieval, given that so many range of instruments.
Yeah.
Good.
Hi, Virendra. Sorry. Very nice talk. And I have a question about the spectrum, the humidity spectrum. And you mentioned that Raman radar is not acting well. And in this condition, does it improve in the clear air condition in measuring this humidity spectrum? And then a relevant question is that given that the limitation of the Raman Lidar, is there an alternative way of measuring this humidity spectrum using other instruments?
Yes, yeah. So thank you for the question. That's a good question. So number one, the LiDAR only gives you mixing ratio only clear sky conditions. So this will be only when you don't have clouds, right? So in between the cloud or below the cloud. So these are only samples from below the cloud when I plotted that. That's number one. The lines here are medians, and the box whiskers are actually from all the hours we have. So a lot of samples went into these calculations. One. So that's first question, I think. Second, answer to the second question is that your, there are ways to improve that, but it's all hardware dependent, and I just don't have. I don't know. People have done this work at the Southern Great Plains site, ARM site, that they believe that Raman Lidar is good enough to get the Q prime, but I have not seen them plot the spectra. That is essentially the in my mind, that's the holy grail. That just tells you yes or no. But they directly went to calculate W prime and Q prime PDFs and instantaneous W prime Q prime values, which I don't think can be done, at least from this case.
So I have this question, which might be simple-minded, right? But I think looking at only vertical velocities, is it possible to, because you own the instrumentation, is it possible to define volumetric elements in the sky and then look at lateral velocities of, like lateral velocities and such? So, or is it in the world of clouds, you don't care about the lateral stuff, especially in cumulus? So is that the case, or is there a value in looking at things in an XY direction as well? I mean, like instead of just vertical. Does that make sense?
There is a huge value looking into that. Absolutely 100%. The clouds evaporate because you have lateral entrainment. So laterally, the clouds are clear air around is entraining into the cloud and evaporate, and the cloud drops. That's a big field of research. The problem is most of the work has been done only using largely simulation models, some modeling work, because from observations it's very hard to do.
I see.
It's extremely hard to get I don't want to, people are here who know more than me in that matter, But but lateral entrainment is a big deal, and that actually controls the cloud lifetime more than the vertical velocity.
I see.
Yeah.
So the EC station that you used to derive the surface moisture flux, that was near the water, so you don't think that there's a contamination from the land going on when you're kind of making that relationship?
The W prime theta V prime, right?
Yeah.
Fantastic question. I know you guys are really good. So that is coming from ERA 5.
Oh.
Yeah.
Oh,
we
okay.
could not do. We do have a eddy correlation flux at the surface system, but that's affected by land, as you just said.
Okay.
So we cannot use
see.
that, and so that's coming from ERA 5, completely separate. And we compare those ERA 5 fluxes to aircraft measurements in the past, because we had a AC in a field campaign, and they compare very well actually.
Oh, cool. Okay.
that's why.
No, that makes sense. Okay. I was wondering, because I figured there'd be contamination.
Yes,
Very good.
Sorry to glance over, but that's pretty good.
No.
Yeah.
No.
Holger.
Thank you. I have one question to your result that your cloud fraction is largely determined by the number of clouds, not by the chord length. You have only a very small amount of data for that.
Yes.
And my question is whether your sampling might have somehow led to that particular result, that inadvertently you excluded all other cases, and that's what you end up with.
It's very possible. I agree with you on that. That's a shortcoming for this work, because you only had 8 cases. We're looking at various sort of marine sector, etc., all of those things, and that's a shortcoming. It might be that only, as you said, that's a consequence of the sampling what we are doing. Yeah, but I don't know how to get around that. That's the main issue. Yeah.
Any other? Yeah. Yeah.
I'll push it all the way to the end. So kind of related to some of the questions, and you also mentioned, I think, in response to Christina's question about variability in the mixed layer depth. So presumably that varied some between the cases. I'm also curious, because I'm assuming for these cases the LCL is located near the top of the mixed layer in all these cases. And I'm wondering if you looked at sort of the variability of mixed layer LCL depth between these cases. And I'm also asking that, getting back again to the chord length, presumably that depends on kind of first order scaling to the mixed layer depth. Like, I don't think it's a coincidence your mean chord length is 500 meters and your mixed layer depth is 500 meters.
Right, it's together, right? That makes sense, right?
Yeah.
Yeah. So, so we have not looked into that. Yeah, we should have. So you're technically saying that the LCL to mixed layer depth will basically control the scatter plot we saw in the cloud fraction and chord length stuff, right?
I think it should be a pretty strong control on the chord length.
Right. Yeah.
In particular, you separate out between moist and dry cases. So I suspect the moist ones will probably have a lower LCL.
Much lower. Yeah.
So,
Much lower. Yeah.
So there should be some variability in there.
The inherent problem I have in this case, Eureka 4, they did similar thing. They had aircraft, so they could move around, and they have LCL variability over a large domain. In here, I'm looking at vertically pointing, and just one value, right? And that's, anyway, that sort of muddies the water a little bit when you calculate LCL at not really from direct, it's very calculated stuff. That's why. Yeah, thank you. Yeah.
Great. Great discussion. Virendra, you should put in one more push. The paper just came out.
Yes. Yeah.
Thank
you. Yeah.
Which journal?
Paper just came out 2 weeks ago in Journal of Applied Meteorology and Climatology. Early on these.
Great. Well, with that, let's thank Virendra one more time.
Thank you.